This video is a summary of the 10th and final topic in AQA GCSE Chemistry, using resources. This includes sustainable development, potable water, extraction of metals, recycling and LCAs, plus the triple science topics of ceramics, polymers and composites, corrosion, the Haber process and NPK fertilisers. You may find this video useful if you're revising for an end of topic test or your GCSE Chemistry paper 2. As we start thinking about the resources that are really vital to humans, it's worth considering a situation where resources are limited and what you would be most worried about lacking. So if you were thinking about living in a refugee camp, there wouldn't be enough food, there might not be enough clean water, you might not have sufficient space, it could be difficult to dispose of waste and that would put you at risk of disease. So when we start thinking about development and resources that humans need, these are the same factors that we're encountering. Sustainable development is development that meets the needs of the current generation without compromising the resources for future generations who are also going to need them. So what this basically means is that we're being responsible with the resources that we're going to use to provide us with warmth, shelter, food and transport, so that the generations that come after us don't have nothing left. Resources can be separated into those that are finite and those that are renewable. Finite resources are going to run out because we're using them faster than they're being produced. This could be because they take a very long time to form, or it could be because it's very hard to make them. Rocks like slate are a good example of this. Slate is a metamorphic rock that forms when a fine clay is subjected to high temperature and pressure, but those conditions don't happen very often, so natural slate is quickly running out, and by continuing to use it for roofing tiles, we are rapidly depleting the supply. Finite materials could also be things that are just very scarce, where demand far outstrips supply, so for instance, precious metals or radioactive sources. In contrast to finite resources, renewable resources are unlikely to run out because they can be produced faster than we're currently using them. This doesn't mean that the supply is infinite or endless, it just means that more of it can be quickly produced. So timber is a really good example of this. We could theoretically use so much wood for making houses and furniture and paper that we ran out of trees, but it doesn't seem very likely at the moment because those trees are growing faster than we're using them. Another way that we can categorise resources is into those that are natural and those that are synthetic. Natural resources are raw materials that already exist in the world without humans needing to do anything, and they're used to provide humans with food, timber, clothing and fuels. Natural resources can still run out though, and that's why they need to be managed sustainably. This might mean limiting how much people can take by having a quota, or providing additional support to ensure that more of that resource can be produced. So this is where agriculture or farming comes in. In some instances, natural materials have been replaced with synthetic materials, which are manufactured from chemicals. This includes making artificial versions of products that already naturally occur, like synthetic diamonds from carbon or synthetic fabrics that replace things like cotton or wool. Or it could include making a completely new material, like making plastics from crude oil. Synthetic materials offer greater durability, which means that they last longer and they don't break down as quickly, at a lower cost, and this can help to protect the limited supplies of natural materials. I haven't included many practice questions in this video because it's really just one big summary, but Unit 10 is prime territory for evaluate or compare questions, so we're going to look at just one. Anywhere in the AQA GCSE Science specification that you have an evaluate question, they're asking you to compare and to write a conclusion. When I look at the data in this table, I'm not just going to quote numbers. I'm going to say which is the biggest of two numbers, and if I can, then I'll compare them, such as saying this one is 5 times bigger. Secondly, I'm going to think, is there anything else I know from the rest of the GCSE that is relevant to this question? I'm not just going to use the data from the table. I'm also going to bring in my own knowledge. And finally, it's vital that you write a conclusion. So I'm going to look row by row at my table, and I can see from the first table that paper uses substantially more water to make 1,000 bags. But I don't just want to say it makes more, I don't just want to quote a value, I'm going to say it takes over 17 times more water. Next, I'm going to look at recycling, and here I can see that paper has the advantage. So I can say that nearly twice as much paper is successfully recycled as plastic. In terms of the disposal, paper is biodegradable. So I can say that what that means is that it breaks down naturally, and that's important because it's not going to be taking up landfill space. Now, because the paper bags can hold 2.5 times more mass. That means they're less likely to break. So over time, I'm going to have to buy fewer of them because they're not going to keep breaking and needing replacing. But then I can also use my wider knowledge and say that crude oil, which is used to make plastic bags, is a finite resource and it's running out. And then, of course, it's vital that I include a conclusion. So here I'm going to say that overall, I think paper bags are better because they're more sustainable, because they're not being made from fossil fuels, and also they're much easier to dispose of. Potable water is safe to drink because it doesn't contain any pathogens, so microorganisms that cause diseases. It doesn't contain any toxins or poisons that would kill us, and it only contains low levels of salts. So that's any mineral, any ionic compound that the water has picked up as it flows through rocks. Now, technically speaking, that potable water is not pure because it does contain some other things, like a little bit of those salts and also maybe some fluoride ions, maybe some chlorine. So potable water isn't pure water. In chemistry, when we say pure, we mean a single element or a single compound with nothing else added to it. The first step in producing drinking water is to identify a suitable source, such as a sea, lake, river, aquifer or reservoir. Now, some of that water may already be potable and safe to drink, but the majority of it won't because it either contains high levels of salt, which your kidneys can't process fast enough, or it will contain pathogens that would cause disease. Once you've identified a suitable freshwater source, in order to make potable water, this must be passed through filter beds to remove any insoluble solids and then sterilised to kill any microorganisms. This can be done using chlorine gas, ozone or UV light. There's a huge amount of salt water in the world in the oceans. Salt water is sometimes called saline, so the process of removing that salt and stopping it from being saline is called desalination. There are two methods that we can use: distillation and reverse osmosis. They're both very energy intensive processes, and that makes them very expensive. So if we have an option to make potable water from other sources, we tend not to do these. Here's an example of the apparatus that you could use to distill water in your lab at school. In the flask we've got the salty water which needs purifying, and there's a heat source like a Bunsen burner which is used to evaporate that water. So the state change that we have inside that flask is evaporation. The boiling point of water is 100 degrees C, so when the water is boiling, that's the temperature that should show on my thermometer. Now the salts and the other substances that are dissolved in the water have a much higher boiling point. So at 100 degrees they don't boil, in fact they haven't even melted, so they'll be solids, so they'll be left behind. The water vapour is then going to flow through the condenser. So a condenser is a hollow tube with a jacket that contains cold water on the outside of it. So as the steam goes through the hole in the middle, it gets cooled down, and that helps to turn it back into a liquid. So as it condenses, the pure water can then be collected at the end in the beaker. And this water won't need sterilising because the same heat that's boiled the water will have also killed any pathogens that are in it. In reverse osmosis, the salt water is forced through a membrane under very high pressure. Normal cellular osmosis is a passive process that you've learnt about in biology, where water molecules move from a dilute solution, which contains very little salt, to a concentrated solution that contains much more. Here we use high energy and high pressure to complete the reverse process. The water is forced through the membrane, leaving the salt behind. The third place that we could get water for making potable water from is wastewater. Urban lifestyles and industry produce large amounts of water that isn't safe to drink straight away, but it can be treated to make it safe. We can split this wastewater into further groups. So sewage is the wastewater from our homes. Not just water from toilets, but also from the sink in your bathroom or your kitchen, plus water from a washing machine or dishwasher if you have one. So that sewage may contain toilet waste, but also washing detergent and obviously toilet paper. Both sewage and agricultural wastewater from farms need to have organic matter removed, and also harmful microbes need to be killed. We've also got industrial wastewater from factories, and that may require you to remove organic matter but also harmful chemicals. Sewage treatment includes 4 key steps. In screening, large debris like toilet tissue is removed by passing it through a fine metal mesh. Sedimentation separates the waste into a semi-solid goo that we call sewage sludge, and then the liquidy, watery stuff on top is called effluent. The sewage sludge is anaerobically digested without oxygen, while the effluent is treated aerobically biologically. The next section in the topic is about novel ways of extracting metals like copper, but in order to understand why we're using these methods, it's important to look at what's happened to the price of these metals over time. So here we've got some data which shows us that the price of copper has risen between 1998 and 2010. To start with, it's risen very slowly, but then from about 2004 onwards, it's risen much more quickly. And the reason for this is that supplies of copper are running out. So the copper that's still available becomes much more expensive because the demand is outstripping the supply. Most metals are extracted from ores, which are rocks that contain enough of the metal compound to make extracting it financially viable. In other words, we can make money from it. Copper is a relatively unreactive metal, and crucially it's less reactive than carbon, so most of the extraction can be done by reduction with carbon. The products of this can later be purified using electrolysis, which is the method we have to use for metals more reactive than carbon, but it's also good for purifying impure metals. Ores can be categorised into high-grade and low-grade ores based on how much metal is in them. As copper has become scarcer, we've had to make increased use of low-grade ores, including those that contain less than 1% copper by mass. Copper that's been extracted from its ore by reduction with carbon is then purified using electrolysis, and this is a very expensive process because it uses a lot of electricity. So you might be wondering, why do we bother doing it? Well, copper is particularly useful because it has very high electrical conductivity and it's ductile, so it's perfect for making electrical wiring. What this graph shows us is that absolutely pure copper with no impurities is twice as good at conducting as copper that has 1% impurities. And so the cost of purifying the copper is offset by how much better it is for its purpose. In other words, people are willing to pay a lot more money for that very pure copper. There are two new methods of extracting metals like copper that you should know about. These are particularly useful if you're trying to extract a tiny bit of metal, say from some soil that's left around a mining site. Traditionally, if you had a quarry or a mine, then to clean up the area afterwards you would use a process called leaching, which involves some pretty nasty chemicals involving cyanide. So bioleaching means using leaching but using living things instead of chemicals. So for bioleaching we use bacteria, and those bacteria remove the metal from the soil and they make a liquid called leachate that contains the metal, and it can then be extracted from that using displacement or electrolysis. So this is a good method because it has very low energy costs since the reaction doesn't require heating, it doesn't release any greenhouse gases, and also it has high extraction efficiency, removing about 90% of the metal that's left in the soil. The disadvantages, though, are that it's very, very slow and there isn't really a way to speed it up. Phytomining is similar to bioleaching in that we're using a living organism to remove small amounts of metal from contaminated soil. We use a kind of plant called a hyperaccumulator, and when it takes up the water in the transpiration stream, it also takes up the minerals in that water and it absorbs the copper. That ends up in the plant's tissues, so to get the metal out we need to burn the plants, and we're left with ash that contains compounds like copper oxide. Then the metal needs to be extracted from that, and the easiest way to do that is to react it with some sulfuric acid and then displace it using a more reactive metal like iron, or use electrolysis again. This is still quite a slow process and it has higher energy costs than bioleaching due to the burning stage and the electrolysis. It will release carbon dioxide as well because we're burning the plants, but we can describe this process as being carbon neutral because even though there's an amount of carbon dioxide that's released at the end of the process, it's that same carbon dioxide that was absorbed by the plant when it did photosynthesis. So in total, no new carbon dioxide is being given out. In biology, a life cycle is a representation of the various life stages that an organism goes through. In chemistry, a life cycle assessment is where a company analyses the life of a product to see how much water, energy and raw materials are used in each stage and what the impact on the environment might be due to things like emissions of carbon dioxide. There are 4 main stages to a life cycle assessment, and then through all of those 4 stages we also have to consider transport and distribution. We consider the environmental impact of the extraction and processing of raw materials, so that could be things like where are those raw materials found. Then we think about manufacture and packaging, so things like what processes are needed for the manufacture. Use and operation in the product's lifetime, so things like what byproducts does using it make, and disposal at the end of its useful life. So that could be things like, is it biodegradable? Is it recyclable? It sounds like a life cycle assessment is going to be very objective and fact-based because I'm going to ask all these questions and accumulate all of this data, but LCAs do have a couple of problems. The first one is that the LCA is carried out by the company that wants to make the product. So they're obviously going to take the more favourable point of view, and they might not be strictly objective. And then the second problem is that some of these things can't really be known or quantified. So for instance, I know that when my product is being driven to its distribution centre, then a lorry is going to be releasing carbon dioxide, but I might not know exactly where the customer is going to be, so I might not know how far that lorry needs to drive. Or I might know that carbon dioxide is released in producing electricity for, say, a computer I'm making to be run, but then I don't know how many hours a day the user is going to have that computer on for. So some of these facts it's really impossible to be accurate with. We can increase the efficiency with which we use different materials in 3 key ways. We can reduce our usage by cutting down on how many raw materials we use. We can reuse things like plastic shopping bags, and also we can recycle things, which means processing them to make a new product. It's a good idea to recycle both for economic reasons, which are going to save us money, but also environmental reasons and socially because we're trying to be more sustainable and leave more resources for future generations. When metal is recycled, it's often just in one big container. So the first thing we need to do is to get out the aluminium. Electromagnets are used to remove all the iron and steel, so the only cans that are left behind are those that are made of aluminium. These are then squashed and shredded into small pieces, and they can be blasted with hot air to remove any labels or inks, so we're just left with the aluminium behind. These pieces are then fed into a furnace at about 750 degrees C, which is hot enough to melt the aluminium, and any impurities in there will rise to the surface and can be scraped off. The pure aluminium cools down and is cast into metal blocks called ingots, which are then sent out to a rolling mill where they can be flattened into thin sheets for making new cans. Once glass has been separated from other recyclable materials using magnets and air suction, it needs to be colour sorted, and this is done using lasers. It's then crushed into small pieces called cullet, and these can be melted in a furnace at over 1500 degrees C. The liquid glass is then divided into gobs, and these can be blown into new bottles and jars. Recycling paper and cardboard is harder than glass and aluminium, and this is because there are so many different types of paper and card which need to be recycled in different ways. So to start with, we need to sort these out. The second reason that it's challenging is that the recycling process fundamentally changes paper. So whereas aluminium cans that are made of recycling aluminium are basically indistinguishable from brand new cans, when you recycle paper you shorten and weaken the fibres. So after you've recycled it maybe 5 times, it can't be recycled anymore because the fibres are just too weak and it won't make good paper. In the recycling process, the paper is collected and transported to a recycling plant, and it's separated out into different types of paper. It's shredded and broken down to fibres, and these are then cleaned and screened. Then the ink needs to be removed and the paper is bleached to make it bright white again. It's usually combined with some virgin fibres, which is what we call the brand new wood pulp that hasn't been made into paper before, and the reason for this is that the recycled paper is not strong enough to make usable paper on its own, and then the combined pulp can be pressed to form paper. You could be asked to talk about difficulties with recycling and how we could increase the number of people who are recycling. So you could think about things like people not knowing how good it is to recycle, and the idea that you could use an advertising campaign to give them more information. You could think about just making their lives a little bit easier by providing more recycling bins. You could talk about the fact that people just aren't motivated, so you could solve that either by rewarding them when they do recycle or by fining them when they don't. And you can also think about the practical side of things. So for instance, with milk bottles, it can be challenging to recycle them because you can't just melt down the green lid and the colourless bottle together, because then you get a lot of very slightly greenish plastic that nobody wants to buy. So we have to actually have humans going through and separating these out. And the same is true of things like trying to recycle copper. Copper is worth lots of money, but there isn't a way to separate it out from other metals other than somebody going through and sorting it by hand. So those are all of the topics for Unit 10 for Combined Science, so if you're not taking Triple Science, you can stop watching the video at this point. Corrosion can be defined as the destruction of materials by chemical reactions with substances in the environment. Quite often when we're talking about corrosion, we're talking about a metal reacting with oxygen and water in the atmosphere and gradually breaking down, but actually the word can describe quite a broad range of different reactions. Rusting is one example of corrosion, but there are 2 important things to bear in mind. The first one is that the word rusting only applies to iron, so it wouldn't be true to say that these copper nails have rusted because they're not iron, they're copper, so instead we say they've corroded. The second thing you should know is that rusting specifically refers to iron reacting with oxygen and water. So if the iron has corroded because it's reacted with something else, that's not rusting. There are a number of different ways to prevent a metal object from corroding, and these mainly revolve around preventing oxygen or water from coming into contact with the metal. In the top right, I've got an iron nail, and because it's currently not protected, over time it will rust. Greasing a bike chain, painting some railings, or electroplating cheap earrings with a thin layer of silver are what we call barrier methods, and they'll prevent the metal from tarnishing and corroding. My second nail here has a layer of red paint around it, and so it doesn't rust. But the thing with barrier methods is they only work for as long as the barrier remains intact. If you get a scratch in the paint like my third nail here, then the metal underneath can still corrode. Some metals form a natural barrier, and one example of this is aluminium. Aluminium is much more reactive than you might expect, but it very quickly reacts to form a layer of aluminium oxide all the way around the surface, and this is very hard and corrosion resistant, so that layer protects the metal inside from any further reactions. Galvanising iron is a little bit different. It's what's called sacrificial protection. The iron is alloyed with a small amount of a more reactive metal, usually zinc. Oxygen preferentially reacts with this because the zinc is more reactive. This is why we call it sacrificial. The zinc is being kind of sacrificed in place of the iron. Even though this does mean that zinc oxide is made, this isn't problematic because unlike iron oxide, which is weak and flaky, zinc oxide is relatively hard and it doesn't break apart. One major advantage of galvanising over barrier methods like painting or greasing is that it carries on offering protection even if the metal gets dented or scratched. The zinc isn't around the outside forming a protective layer, it's mixed right in with the iron, and the way it works is because the zinc is more reactive. However, galvanising won't last forever. My incinerator here has got hot enough that all of the zinc has reacted, so it's basically been used up and now the iron has begun to rust. An alloy is a mixture where the primary component is a metal. Pure metals and alloys have different properties to one another. Alloys are harder. If we look at a pure metal at an atomic level, all the ions are one size because they're all the same element and they form these regular rows. So if you hit a pure metal with a hammer, it's possible for one of those rows to slide over the other rows, and therefore this makes the metal malleable. If you compare that to an alloy, the ions are different sizes because they've come from different elements. So therefore the regular rows are distorted, and if you exert a force on an alloy, those rows can't slide over each other, and this makes alloys harder. Alloys are one of the named examples of a formulation, which you met in Unit 8 in the chemical analysis topic. So they're mixtures that have been designed as a useful product with really carefully measured quantities of all the different components. There are 7 named examples of alloys that you need to be aware of. So bronze is made from copper and tin and it can be used to make coins. Brass is made from copper and zinc and is used to make the pins of plugs. Gold can be alloyed both to make it cheaper but also to make it harder. And then there are various different kinds of steels. So high carbon steel is strong but brittle, so it's useful for cutting tools where it's always working in the same direction and there isn't going to be any unexpected stress in different directions. Then low carbon steel is softer and it's more easily shaped, so that's useful for things like making car bodies. Stainless steel contains chromium and nickel, and these help it to resist corrosion, so it's useful for cutlery, which may be exposed to acids in our food. And then aluminium alloys have very low density, so they're useful for building aircraft. Ceramics are non-metallic solids made from a raw material that's then heated to a very high temperature. The 2 types of ceramic that you need to know about are clay ceramics like pottery, which tend to be opaque, and then glass, which is then transparent. Both of them are hard and waterproof, but they're also brittle and they shatter easily if you drop them. You could be asked about the uses of ceramics and the properties that make them appropriate for that use. Also, we could talk about different types of glass ceramics. So there's soda lime glass, which is used for everyday uses like making windows and tumblers for drinking out of, and it's made from sand, sodium carbonate and limestone. But it doesn't have a very high melting point, and that could be problematic if you want to use it for something that's going to reach a very high temperature. So for heat sensitive uses in the lab or in the kitchen, you have hard glass, which is borosilicate glass, and that's made from sand and boron trioxide. A polymer is a very long chain of repeating units called monomers, and that word very is essential if you want to get the mark for the definition in the exam. These monomers aren't individual atoms, they're small covalent molecules that are then formed more covalent bonds between them to make these very long chains. Within one chain of polymer, there are strong covalent bonds, and then between two chains, there are weak intermolecular forces. These are the same weak intermolecular forces that you would see between two ammonia molecules or two oxygen molecules, but actually polymers tend to be solids at room temperature. And the reason for this is that these polymer molecules are much, much bigger than ammonia or oxygen, so therefore the weak intermolecular forces are comparatively stronger. We can name these polymers based on the monomer they're made from. So if I take 1,000 ethene molecules, I could make polyethene. And if I take 1,000 propene molecules, I could make polypropene, and so on and so forth. In Unit 7, you met the idea of addition polymers and condensation polymers. So just to quickly remind you, an addition polymer is made from monomers that have a double bond in the middle, and that double bond is going to break, allowing each one of the carbon atoms to form a new bond, and therefore it can bond to a monomer on either side, and we get this very long chain. Whereas in condensation polymerization, we need two different functional groups. So this could either be two different monomers that need mixing together, or it could be one monomer that has a different functional group on each end, like these amino acids here. I have an amine on one end and a carboxylic acid on the other end, and the condensation polymerization will involve the loss of a small molecule like water and the new bonds forming. Also in Unit 7, you learned a range of examples of polymers, including DNA with its double helix structure made of 4 complementary nucleotides, proteins made of amino acids, shown here on the right by the amino acid glycine, and starch, which is made out of the monomer glucose. Now, polymers can have different properties, like different melting points or flexibilities or densities or tensile strengths. And those properties will differ firstly based on the monomer that they're made out of, and then also the reaction conditions when that polymer was made. So that means the temperature and the pressure and the catalyst used. Polyethylene is a really common, very useful plastic, and there are two main types. There's low density polyethylene or LDPE and high density polyethylene or HDPE. Low density polyethylene is made under very high pressure and pretty high temperature too, with a tiny bit of oxygen in there as a catalyst. And when the polymer forms, it makes these long branches, and those branches stop the main chains from packing too closely together. In contrast to that, high density polyethylene is made under relatively low pressure, maybe only 10 atmospheres as compared to 1,000, and a slightly lower temperature, probably about 100 degrees C, with a kind of catalyst called a Ziegler-Natta catalyst. And when it forms, the polymer chains get into these really regular rows that can pack tightly together, and so the final polymer is much harder and much denser. Now, completely separately from that, you need to know about thermosetting and thermosoftening polymers, and I really want to emphasise this is a different part of the specification. So in thermosetting polymers, we don't just have these branches that are keeping the chains further away from each other. We actually have covalent bonds between one chain and the next, and we call these crosslinks. Now, if a polymer has these crosslinks, it's described as thermosetting, whereas if it doesn't have them, it will be thermosoftening. So as the name suggests, when a thermosoftening polymer is heated, it softens and it melts. Whereas if a thermosetting polymer is heated, then it doesn't melt, instead it chars and burns. A composite material is made by combining two or more raw materials. So we're not talking about grinding them into tiny pieces and blending them together. There are still quite large, distinct parts of each, but each of them is contributing a property that gives us a useful combination, like being very strong and very lightweight. The two individual materials that make up a composite are called the reinforcement, which tends to be the bit that's providing the strength, and then the matrix, or it's sometimes also called a binder, which is kind of holding the whole thing together. The Haber process is an industrial chemical process used to make ammonia, this molecule on the right, NH3. Ammonia is really important because it's the main component of most of the crop fertilisers that our farmers use. It's a gas at room temperature, and it's made out of hydrogen and nitrogen reacting in a 3:1 ratio in this reversible reaction. In order to get that hydrogen and nitrogen, the nitrogen is just extracted from the air, but it does need to be separated from the other gases, because if we tried to use air in the Haber process, then the oxygen would react with everything else and we wouldn't get pure ammonia. There are a couple of different ways that we can get the hydrogen, but the most common way is for it to be extracted from methane by reacting it with steam. This makes carbon monoxide and also the hydrogen. In order for the reaction to take place, the mixture of gases in that 3:1 ratio is fed into a reactor, and there they react together in the presence of a hot iron catalyst at a temperature of 450 degrees C and a pressure of about 200 atmospheric pressures. So that means 200 times the normal pressure that is in the room with you right now. The iron catalyst is used because it helps to speed up the rate of reaction without needing to heat things up any further. So that's going to reduce the energy costs and be better for the environment. The other two conditions are a little bit of a compromise, so we're going to look at why and how they're used. The Haber process is an example of a reversible reaction, so we're going to have both the forward and reverse reactions happening at the same time, and the aim is to produce as much ammonia as possible. Well, if I count up the number of molecules on each side of this equation, I can see that I have 4 moles of molecules on the left and 2 moles of molecules on the right. So Le Chatelier's principle says that as we increase pressure, this is going to favour the reaction that reduces pressure, which here is the forward reaction. So this will move equilibrium to the right and increase the yield. So high pressure is a good thing for producing more ammonia. However, high pressure is also going to be dangerous because it increases the risk of explosions, and also expensive because it means that we're going to have to buy equipment that can withstand that high pressure. So therefore, we don't push the pressure any higher than 200 atmospheres because of those reasons. The forward reaction of the Haber process is exothermic, and that means that raising the temperature leads to a lower yield. I make less ammonia. So from a yield point of view, a colder reaction would be better. But a colder reaction temperature also makes the reaction slower. So if I did the reaction at room temperature, I could make loads of ammonia, but it might take me a year. So instead, I pick a compromise temperature. I use 450 degrees, which gives me a yield of about 15 to 17%, which still doesn't sound great, but it's at least happening at a fast enough rate to make it economically worthwhile. Because only about 15% of the nitrogen and hydrogen in the reactor is going to make ammonia, what comes out at the other end is a mixture of gases. We need to separate the ammonia as a product from the leftover nitrogen and hydrogen so that they can be recycled back into the reactor to try to react again. The mixture of gases is pumped into a condenser to cool them down to a point where the ammonia becomes a liquid, but the nitrogen and hydrogen are still gases and therefore easy to separate. Fertilisers are substances that farmers spread on their crops in order to make them grow faster and increase the yield, so they're producing more food and therefore producing more money. They do have some disadvantages though. They can be quite expensive and spreading them on is time consuming, but also if you add too much it can cause major environmental problems. When it rains, any excess fertiliser will run off into nearby rivers and lakes and cause a problem called eutrophication. Algae that are already living in that river or that lake will take that fertiliser and reproduce like mad and create what's called an algal bloom. And when that then dies off because they've now run out of fertiliser, then bacteria in the water will break them down, and in doing that they're going to use up all of the oxygen that's in the water, and this causes the water to be deoxygenated and it causes aquatic life like fish to die. NPK fertilisers are synthetic fertilisers. In other words, they're not natural like manure, they're made from chemicals in labs. They're an example of a formulation, so this is a mixture that's designed as a useful product, and they're going to have really precisely controlled amounts of nitrogen and phosphorus and potassium, which are all necessary for plants. NPK fertilisers don't contain the raw elements nitrogen, potassium and phosphorus. They contain compounds that have those elements inside them. So you already learnt that in the Haber process, ammonia can be made, and that ammonia can be used to manufacture ammonium salts and nitric acid, both of which contain nitrogen. The potassium and the phosphorus have to be mined out of the ground in potassium chloride, potassium sulfate and phosphate rock. The potassium chloride and potassium sulfate are soluble, so they can be used directly in fertilisers, but the phosphate rock can't because it's a rock. So we have to do something called the Oder process, in which you take your phosphate rock and treat it with either nitric acid or sulfuric acid. And because phosphate rock tends to contain quite a lot of calcium phosphate, this reaction makes phosphoric acid, which is then going to contain our phosphorus, and also calcium nitrate or calcium sulfate. And it's the phosphoric acid that we want that's going to be added to the fertiliser as a source of phosphorus. Apart from just asking you to remember why fertilisers are used and what NPK fertilisers contain, you might be asked to compare and contrast different types of NPK fertiliser and which one would be more likely to be used and which one would be cheaper. So for instance, here we can say that making ammonium phosphate requires more different raw ingredients, and also it requires more steps. But ultimately, a farmer is likely to use both of those compounds together because crops need nitrogen and phosphorus and potassium for their best growth, and so the two fertilisers between them contain all three elements. It's also a good opportunity for testing out some math skills, so things like asking you to use percentages and say, well, if this fertiliser contains 5.8% potassium by weight, then what mass could be extracted from a 3 kilogram box? So then working out that that will be 0.174 kilograms and then converting that to grams. Likewise, as well as testing out your knowledge of percentages, they could test out your maths knowledge of ratios. So here we've got 9 parts nitrogen to 15.8 parts potassium. So if we've got 270 grams divided by 9, that means 1 part would be 30 grams, and therefore 15.8 would be 474 grams. Thanks very much for watching, and I hope you're now feeling a bit more prepped for GCSE Chemistry Unit 10. Good luck for your exams, and if you did find this video useful, don't forget to like, subscribe, comment and share for more GCSE revision videos coming soon.